Greetings! This is Stephanie joining you for this special episode, and welcome to the First Global Podcast. For today's episode, we're highlighting some team activities and interviewing Carlos G. Niederstrasser from the Northrop Grumman Corporation about the exciting area of CubeSats. Stay tuned to hear about the kinds of opportunities this technology offers. As part of the In the News social media challenge, for 2 weeks, teams have been in the media spotlight, featured on the radio, in print and website articles, and on broadcast TV, all highlighting their activities for the 2021 First Global Challenge. Way to go, teams! Today we are wrapping up the Solutions Challenge with the conclusion of Phase 3. Alliances are submitting their engineering notebooks and summary videos, highlighting their collaboration and final solutions. For the next step, judges will review all of the submissions and select the winning alliances. Teams still have 10 more days to work on the CubeSat Prototype Challenge and Robotics Challenge, both of which will wrap up on 28 September. The students are all hard at work to complete their challenges before then. As they work to perfect their CubeSat prototypes, a few have also taken the initiative to organize information sessions with professionals in aerospace and CubeSats. Team Tunisia also started their own workshop series to teach other teams what they've learned so far. This leads us perfectly into our interview. For today's episode, we are joined by Carlos G. Niederstrasser, a space systems architect at the Northrop Grumman Corporation, which is a multinational aerospace and defense technology company pioneering advanced products in air, cyber, land, sea, and space domains. First Global teams are building their own CubeSat prototypes as part of this season's activities, so we're excited to learn more about this technology at the industry level. Thank you for joining us, Carlos.
Thank you for having me. It's a pleasure.
Well, I guess we'll get started with our first question. Can you tell us what being a space systems architect means and what kind of work you do in that role?
Absolutely. So at Northrop Grumman, I basically help develop new concepts for science and commercial and national security missions that involve space applications. That usually means coming up with the original concept that would meet our customers' needs, developing what the spacecraft would look like, as well as doing the general initial analysis of what the system will, how the system will perform.
Okay, our second question is, what are some of the applications for CubeSats?
No, that's an excellent question because it has changed so much over the past few years. Originally, CubeSats were really designed as an educational system. They were meant to allow students to develop an entire satellite in a very short time frame that was suitable for the university environment. But as technology has developed over the last 10, 15 years since CubeSats were introduced, and as more and more CubeSats have come into play, we really are finding out that CubeSats can do almost everything that larger satellites can do, maybe in a slightly different fashion or with different performance metrics, but they can really do anything that we set our minds to. So there's been CubeSats that have been used for Earth observation. There's CubeSats that are used for telecommunications. There's even been interplanetary CubeSats going to Mars and conducting interplanetary science. So really the gamut of CubeSat applications is really as broad as the gamut of space exploration itself.
Okay, that's pretty interesting. Our next question is, what does the process and timeline look like for creating and launching a CubeSat?
I would say that really depends a lot on the CubeSat's mission as well as the organization that's building the CubeSat. If it's a university building CubeSat for the first time, and we have a lot of those around the world, just a couple years ago, for instance, Guatemala launched its very first satellite, and it was a university CubeSat. Oftentimes, when it's a university building it for the first time, it can take 4 or 5 years. And that's just due to the usual learning curve, the students coming in and out of the program, and all the usual student challenges. They're not only working on the satellite, they're also working on their classes and trying to get good grades and so forth. As the process evolves and maybe a university starts building a second CubeSat, or if we have a corporation building it, especially if they're using a lot of off-the-shelf components, that can often be done in as little as 18 to 24 months. So it'll really depend on the resources, it'll depend on the team, and to some extent it'll depend on the mission. Like much larger satellites, especially for science type missions, the driving element of the schedule tends to be the payload and the scientists developing the payload. So that often will stretch the schedule, even though the rest of the CubeSat might be ready to go.
An important part of any project is prototyping, experimenting, and learning from failure. Do you have any examples or insights into this from your experience?
Absolutely. So the first satellite, or fake satellite, if you will, I worked on was just that. It was a prototype that we did as part of my spacecraft design class in graduate school at Stanford University. Before the professor would let us touch any real satellite hardware, in the first semester, we had to design what we call the CubeSat. Kiwi, as you know, is a bird that is unable to fly, and that was why we chose the name of the CubeSats. They were satellites that were never meant to fly. And the electronics of the satellite were real electronics. The structure might have been plastic or cardboard, but all of these CubeSats have had a specific mission that taught us all of the basics of a satellite: communications, the payload, the power, the computer, and so forth. And we put the satellite through a mock launch where we stuck it into a garbage can launch vehicle, and we shook it around and pretended it was an actual launch event, verified that the satellite didn't get damaged in any way, and then proceeded to operate it and conduct its mission. So it was really meant to emulate the real testing and the real environments a satellite might go through without playing with the very expensive space hardware. But that sort of philosophy carries on to professional hardware satellites. When we're building a satellite in Northrop Grumman, we use two philosophies. One of them is test like you fly and fly like you test, meaning that you really want to test as closely as you can to the way the satellite will be operated in space. And once you're in space, you want to fly it the same way you have tested it. You don't want any surprises. But we also do something called test early and test often. You don't want to wait until the last minute to be testing. You want to be testing individual components and subsystems very early on. The more you test, the higher your likelihood of success. And we see that with CubeSats as well. There's been studies with CubeSats. The satellites that have been tested the most tend to be the most successful. Now, tying it back to FIRST and FIRST Global, I've been involved with a number of FIRST teams. My daughter was in the FIRST robotics team, and I see the same thing. In general, the teams that tend to be the most successful are the teams that really are able to do a lot of testing. If you wait until 3 days before the due date, the competition date, the launch date to start doing all your testing, you're going to find out that you run into issues, or you need to wiggle it a little bit to make it work. And that ability is not present once you launch a real satellite or once you're in a competition. So that early testing and testing a lot is so important to developing hardware like this.
Okay, that actually leads us right into our next question. What are common challenges to overcome when dealing with CubeSats?
Okay, there's a number of challenges that we see across the board, some of them which are mirrored in larger satellites as well, or other large technical projects. One of them is the interaction between software and hardware. A CubeSat, a satellite, a phone, even a dishwasher nowadays, it's a computer at its core. And that means it's got software, and software that has to talk to a lot of the hardware. And that ends up being a real concern in just making sure everything works and making sure, again, it's thoroughly tested. Another common challenge, especially for university CubeSats, it's documentation. Engineers do not like to necessarily write documentation and write what they've done. And that becomes so important, not only when you run into problems, but when you have turnover in teams and in schools, both high school, universities, it is so common to have turnover where students come in and out of a project. And so that documentation and being able to write down what you've done so someone else can go pick it up is also very important. The final thing I would say is, especially today, a lot of CubeSats are being built with off-the-shelf components. You can go to various websites and various manufacturers and buy almost all of the components you need to develop a CubeSat. Before, you usually have to build them on your own. What happens, though, is you get all these components, you try putting them together, and you quickly realize that maybe things don't work out quite the way you expected them to work. That interfacing of components, interfacing a computer with a radio, maybe from a different vendor, you suddenly realize that on paper, they both indicated they used the same protocols or the same connector type. You put them together, and all of a sudden you realize that, oh, the protocol's a little bit different, or maybe I was expecting a slightly different way of formatting the software, or any number of things. And so that interfacing ends up often being a challenge when it doesn't work the way you thought it would work.
Okay, I think our teams are all experiencing a little of that, both with the documentation side and also all of these off-the-shelf components that they received in their CubeSat prototype kits, and finding out from these different manufacturers how to make them work together.
I can imagine that, absolutely.
So our next question is, how can CubeSats be used to tackle broader challenges, such as those related to environment or health?
Well, I mean, broader challenges, of course, is a huge spectrum. Now, health, of course, will be a lot more challenging, simply because CubeSats are so small and they don't involve human beings. There have been some CubeSats, I believe, that have tried flying some sort of biological payload, but really, on the health side, it can be a challenge just because of the nature of the CubeSat. But for the environment, you have a lot of CubeSats today doing real science that directly ties into the environment. Almost anything that is observing Earth from space, in some way or another, is helping us better understand the Earth's environment, whether it's climate change, whether it's weather patterns, whether it's pollution. So much of what we know related to that is coming from space, and CubeSats are no exception. You can use CubeSats to try to just do direct imaging, right? In fact, Planet is a very famous constellation that has hundreds of CubeSats they have launched over the year. Each one of them is about the size of a loaf of bread. And they've been imaging, because they have so many satellites, they've been imaging the entire Earth on a daily basis. And they will often publish pictures that compares a before and after image due to a natural disaster like a hurricane or an earthquake. They've published before and after pictures of deforestation due to mining or due to industrial development or residential development. So it really allows us to see how both the Earth's weather itself or humans are impacting the Earth's surface. Similarly, we can use CubeSats to observe the ocean. We can use CubeSats to take measurements of the atmosphere. One interesting mission I've been recently involved with out of New York University in Abu Dhabi and United Arab Emirates in the Middle East is actually trying to detect gamma rays that are emitted from thunderstorms. So normally we're used to gamma rays coming from deep space, but it turns out that lightning and thunderstorms will also emit gamma rays. So the hope there is that watching these gamma rays coming from the thunderstorms will give us a better understanding of the physics and science behind thunderstorms. And of course, thunderstorms are some of the deadliest weather events. They can often produce hail, tornadoes, and flooding. And so being able to better understand thunderstorms directly impacts our ability to potentially save lives in the future.
Very cool. I did not know CubeSats could be used for detecting things like that on the ground. So it's very interesting work you're doing. Our next question is, what exciting opportunities do you see for the future of CubeSats?
I think the opportunities are as big as space exploration in general. like we started off the conversation, CubeSats really are doing such a broad array of things today that it's really up to the imagination of the scientists, the engineers, the students that are working on these CubeSats as to what can be done. Planet has already shown that we can put a constellation of hundreds of CubeSats around the Earth. What if we could put a constellation of hundreds of CubeSats around Mars, all taking measurements of the Martian atmosphere? Now, Mars has seasons just like the Earth. It has global dust storms that slowly envelop the whole planet. Of course, we have studied Mars a lot with rovers, with landers, with orbiters. But fundamentally, all of the missions we have sent to Mars, for instance, are located in one point, whether it's a rover that's moving a little bit or a single satellite that's in orbit around the planet, they're still in one point. If we could have simultaneously 100 CubeSats studying the Martian atmosphere, we'd get a better understanding of the overall dynamics of that atmosphere. So that's just one example. Now that we have shown that CubeSats can be flown interplanetary, which was done a couple of years ago, again, more applications around the Earth. We're getting CubeSats that are being used to observe other satellites, something called space situational awareness. Very important for the military, obviously, knowing where all of the satellites are. But as more and more satellites go up in space, we could also use them to observe other satellites just to help ensure the safety and of the entire orbital environment. As the Artemis program continues to evolve with lunar exploration on the moon, and as we send the next set of humans to the surface of the moon, CubeSats again could be helping to serve as localized communication relays, or they could be carrying out observations in parallel with astronauts on the surface. So again, it's a wide range of applications, and it's only going to get more exciting as our technology gets better. When we look at the first CubeSats in the early 2000s and CubeSats today, they have benefited from the same thing that we have benefited in our cell phones, in our at-home technology. All the electronics have gotten faster, have gotten better, have gotten smaller. They use less power, they're lighter. Well, all of that allows CubeSats to do a lot more today than they could 20 years ago when they were first being thought of.
Okay. So our final question is, a lot of our audience includes youth who are interested in a career in STEM. What advice do you have for students who might be considering a path similar to you, or more generally in STEM?
So I think the number one thing going into career in space is to realize that, yes, you can do it. There's so many times when we run into obstacles that tell us, no, you didn't do well in your math test. No, girls cannot do this. No, you're too young to get involved in a project. So yes, you can do it. Now, what is it that you can do? Of course, you ought to do well in all your STEM-related classes, math, science, physics, chemistry. But I think it's also important to try to get hands-on experience of any sort, even when you're young. And that can take a wide variety of ways and you can do that. As young as 7 or 8 years old, you can start learning to code, whether it's using platforms like Scratch Junior or Minecraft that teach you how to code and write software. As I mentioned earlier, today, everything is a computer. Even your refrigerator has a computer inside of it. So learn to code early. Legos. Legos have all sorts of building activities. There's robot kits for Legos where you can start developing robots that you can learn about gears and about batteries and about sensors and actuators and how you make a robot move around in response to its environment. Join clubs in school that allow you to work with other students and other kids that have similar interests. FIRST is an excellent example of that, whether it's FIRST Robotics or FIRST Global, where you're actually building something and you're realizing, oh, wait, my robot didn't work the way it was supposed to once I put it into real competition field, but it looked so beautiful and it always worked in the lab. What happened? Well, now I know I need to test more. So everywhere along the way, there's so many opportunities, some of which are very low cost or even free, like being able to code in Scratch. If you can get your hands on a computer, whether it's your own or at the school or at the library, you can start to learn and be more involved in STEM activities right away at a very young age and throughout your elementary, your middle school, your high school, your college career. One of the reasons I went into the graduate program I went to was because they were building a student satellite. It was the predecessor of CubeSats. So this was a little bit before CubeSats were invented. It was being run by Professor Twiggs, one of the two co-inventors of the CubeSat. And I chose that program specifically because I knew it would allow me to get hands-on experience on real hardware. I could have gone to other graduate schools, but not necessarily gotten that hands-on experience. And I think that is so important throughout your STEM career. And it really prepares you for each step of the way as you progress into more advanced schooling and ultimately into your professional career.
Okay, well, thank you so much, Carlos. We really appreciate your time and your excellent insight into this. It was really great meeting you.
It's a pleasure, and I was glad to be able to participate. I wish all of the First Global teams the best of luck. I know how exciting it is to build, even if it's just a little prototype CubeSat. Don't think because it will never fly into space that it's not worth your time. It is so exciting just to see the finished product actually transmitting signals, doing what it's supposed to. And even if it doesn't work the way you want it to, you still learned a lot along the way. And the next time you can do it even better and make sure it accomplishes the goals you've set out for it.
Well, thank you.
Thank you.
And thank you to all our listeners for tuning into this episode. Make sure to subscribe to catch our final episode next week. Until then, let's continue to discover and recover.